He is a prolific writer. He wrote King of Salmon, he wrote Dirt, The Hidden Half of Nature with his wife, Anne Blithley. And tonight we're going to hear about his book, The Growing Revolution and Bringing Our Soil Back to Life. And this book is really a good read. It talks a lot about why this is important and how it improves productivity of the crops that are grown in healthy soil, how it can sequester carbon and actually address some of our climate change concerns. So there's just a lot of really good things about making your soil healthier and increasing your organic matter in the soil. So David's going to go into this in detail, so I'm going to hand it off to him to get started.
Okay, and I will, let's see if that just, okay, that, you touch it and it moves. Well, thank you all for coming tonight, and thanks to the Conservation District for asking me to come back out here, and thanks to Griffin Bay for showing up with a box full of books, which I obviously recommend to all of you, but I have a complete conflict of interest in that. Just, you know, I'm a geologist. I'm not a soil scientist. I'm not a farmer. One of the things that I'm going to try and do tonight is explain to you why somebody like me would have written 3 books now about soil. Because 10 years ago, when I wrote Dirt, the Erosion of Civilizations, the book up there on the left-hand side of the screen, I was really interested in looking backwards through history, the way that a geologist is trained to do back through Earth history, and look at the role that soil erosion and soil degradation had played in ancient civilizations. And so I was looking at archaeology and geology and combining it to look at history, and that got me sort of interested in thinking about soil in a different way. Because as I'll go into a little bit in setting the stage for why I just wrote Growing a Revolution, that got me really thinking about humanity's long-term relationship with the land through soil mediated through the act of farming. And so that got me interested in the whole arena. The middle book, The Hidden Half of Nature, that Anne and I wrote together, really was our exploration of sort of how soil fertility really works in the way that we understand it today, you know, 20 some odd years after she and I were in a graduate soil science class together, looking at what is the role of microbes and the life in the soil in really maintaining fertility. Our views of that have changed a lot in the last several decades. And Growing a Revolution, the new book, is really an exploration of how to apply some of those ideas and principles that came up in the second book to the larger problem of farming globally. And for that, I went around and visited farmers around the world who were restoring fertility and life to their soil and tried to ask the questions of, well, what did you do? How did it work? And try to then step back and look at the commonalities to look at, well, could we really restore soil at a global scale? That's what I'm going to get into. If you're into Twitter, we're at Dig2Grow on Twitter. Feel free to live tweet the talk. But let me get right into it. So as I started looking into the problem of soil degradation, I really realized that we should be thinking about soil as a strategic resource, and it is one that we don't tend to think of that way in the way that we think of, say, oil or the climate or fresh water. Yet it's every bit as important and strategic at the scale of, you know, at civilization building and demise scales as those other things that we think of as strategic resources. And if we look at the state of the world's soils, as we will in a moment, we can really argue that the global soil degradation is one of the most underappreciated, if not the most underappreciated, environmental crisis that humanity faces today. And why can I say that? Well, if you look at the state of global soil degradation, it's something that can be viewed as quite sobering. If you think as a geologist over long periods of time, like 50 or 100 years, actually being short periods of time in the terms of the grand sweep and scope of human history and the history of the Earth. This shows you the map that the UN put out a few years back about the global extent of soil degradation. You'll notice that there's an awful lot of this red color, areas with very degraded soil around the world. A lot of the rest of the world has degraded soil. In 2015, the UN put out a supplemental report about the global state of the world's soils that argued that humanity is losing 0.3%, or about 1/3 of 1%, of our capacity to produce food each year due to degradation, ongoing degradation of soil around the world. And that's a cumulative number, each year another 0.3%. And if you play that out, we only have a couple hundred years at the most left of productive farming in the world if that trend continues. Now, I'm not arguing that that will continue, because it can't. There's far too many people in the world. Something will change. And the thesis of the new book, Growing a Revolution, really is that agriculture is going to be changing in the 21st century. The question is how. Will the current trends of a growing population and a declining amount of a fertile farmland and our ability to feed that population intersect, or will we fundamentally change the way we farm and actually avoid that kind of a societal collision down the road? What's the extent of global soil degradation? David Pimentel and colleagues back at Cornell back in the 1990s estimated that since the Second World War, over the sort of the latter half of the 20th century, the world had lost some 430 million hectares of farmland to soil degradation. That's an area about the size of China and India combined. About 1/3 of all the world's cropland. Now, if you think about the problem of feeding the future, if we could actually have that 1/3 of the world's cropland restored back to its original fertility, it would be a lot easier to feed the next several billion people that we're going to be hosting on this planet by the end of this century. And the numbers from the UN that I mentioned a minute ago down there at the bottom of the screen. So this is the kind of background that I sort of looked at in trying to get into writing the Dirt book, which looked at civilizations around the world and tried to look at what had happened in the past. Because one of the things that geologists tend to do is that we look for lessons in history, lessons in the past about what we might actually expect to be playing out in the future. And I went around and looked at the archaeological evidence, tried to synthesize that for societies around the world. And the pattern that I recognized was that there was a very similar story to many civilizations around the world, in that soil erosion and degradation played a role in the demise of ancient civilizations, back from Neolithic Europe or Bronze Age Europe to classical Greece, Rome, the southern United States. There was a whole socioeconomic setup to the Civil War that we don't tend to teach in high schools that had to do with land degradation and plantation agriculture. Again, read the book if you want all the details. It's a fascinating read. That it was a lot of stuff that I didn't know, wasn't taught in high school or college, but this way that people have treated the land has created and set up the circumstances that center around the rise and fall of civilizations throughout history. There's some exceptions, of course, and I'll go into those a little bit in a few minutes. But there's this real pattern throughout human history that societies that did not take care of their soil did not stand the test of time in the way that a geologist would look at it. What was really the problem? Well, if a nonfiction book can have a villain, the villain of the Dirt book was the plow. And why would that be? Well, the invention of the plow fundamentally altered the balance between the production of soil and erosion at the surface of the earth. And if you sort of wonder how that might work, think about what a plow does in terms of turning the soil over. It makes it really good for weed control. It makes it good for preparing a seed bed for planting. But it also leaves the ground vulnerable to erosion by wind or rain for some period of time before the next crop or weeds, whatever comes back, comes back. And if you look at the pace of soil production, the pace at which rocks break down to make soil, how many of you have ever taken a rock and just set it out on a street corner somewhere and waited for it to become soil? Yeah, one, okay. Not many of us, a lot of geologists have run that experiment, but we kind of expect, our great-great-great-great-great-grandchildren to finish up the study for us. It happens really slowly. Nature makes soils at the pace of about, to make an inch of soil, the conventional wisdom that's actually a pretty decent global average is it takes 500 years to maybe 1,000 years to make that, for nature to make that inch of soil. You can erode an inch of soil off of a cultivated landscape in well under a century. You could actually do it, as I'll show you data for a little later, you could do it in several decades actually. And that's been done time and again through human history. So what is it, if you sort of look at this in a less abstract and more concrete manner, the way a geologist would, about the problem of soil erosion, this picture of a winter wheat field in the Palouse over in eastern Washington really captures why a geologist would look at the problem of tillage-based agriculture as a fundamental problem over the long run on any kind of sloping land. There's very little perfectly flat land in the world. But so this, you'll notice all those little channels carved into the landscape. Those are called rills in the sort of geomorphological parlance. They're things you could plow right across. You could erase them quite readily with agricultural implements. But a geologist looks at that and sort of goes, wow, the soil is just bleeding off the landscape. And how significant can those little rills that can recur year after year actually be? They can add up to huge effects over time. This shows you a winter wheat field also in the Palouse, which was originally where the grassland was broken in 1911. That fence up there surrounds the water cistern that the farmer, the fence was built around the water cistern to protect it from the effects of tillage. The only thing that actually happened in this field for the next 50 years, from 1911 to 1961, is that it was regularly plowed. 1 year left fallow after plowing the next year. Those kind of rills came in, and this little black thing right there is a 1 foot increment on a survey rod, a stadia rod. What this shows you is that a 5 foot cliff developed at the edge of this field over the course of 50 years, simply as a result of agricultural practices. Now, 5 feet in 50 years, that's about a foot a decade, that's about an inch every year, more or less. There's nowhere on Earth that soil forms that fast in nature. Nowhere. Now you should be sitting there thinking, well, this is a really extreme example. Of course it is. That's why I'm using it. It makes it a good teaching device. You should be asking the question of how typical is this? Well, it's not real typical in terms of that extreme number, but the basic message still comes through. And I'll show you more numbers in a moment, but there's an example from our own history in the United States that actually tries to ground the idea that agricultural-based soil erosion could limit the fertility and economic viability, the ability to produce crops of a whole region, is actually not a crazy idea if you just give it enough time. This shows you a map of the American Southeast from Virginia up here all the way down to Alabama over there, and that gray noodle in the middle is the Piedmont hill country, the upland country. It's not the relatively flat coastal plains. It's not the high country of the Appalachians. It's the hill country, the sloping terrain in between. And it shows you the amount of soil erosion that's been reconstructed to have happened since the dawn of colonial agriculture in the American Southeast. And you'll notice that most of it's gray. The legend tells you that's 4 to 10 inches of soil loss. The black stuff, that's about 10 inches or more of soil loss. Well, how big a deal is that? There was only about a foot, 12 inches of original thick black topsoil across this region when the area was first plowed back in the 17th century. So if we could erode off, primarily through tillage-based erosion, and the effects of rainfall falling on plowed fields, if we could erode off a third to almost all the topsoil in about 200 years, think what the Romans could do with a 1,000-year run at the hills of central Italy. Think about where the port of Rome, Ostia, sits today. It's miles inland from the coast. And that's not because sea level has been falling, it's because all that soil washed off the hills of Italy has been building out into the Mediterranean, and the port is now abandoned well inland. I've actually visited farms in North Carolina up in sort of this area. It was featured in a Nova show, Making North America, episode 3. There's this great little visit to a tobacco plantation in North Carolina, and one of the reasons we went there is the topsoil is literally gone. They're farming the subsoil, and you can just compare the soil in the forest right next door with the contemporary tobacco field, and it's like night and day. Well, those kind of changes, the degradation of soils in the American Southeast, were widely recognized in colonial times. George Washington and many of his plantation-owning contemporaries were actually very concerned about the state of American soils at the start of the country that we now inhabit. And what they were basically complaining about was that their yields, their crop yields, the productivity of their fields was much less than in their grandparents' days. And so Washington was trying to fill in gullies. He started experimenting with crop rotations and cover crops to try and reduce erosion and try and build fertility, but they still were very much engaged with the plow. And he basically wrote in a 1796 letter to Alexander Hamilton that a few years more of increased sterility will drive the inhabitants of the Atlantic states westward for support, whereas if they were taught how to improve the old, instead of going in pursuit of new and productive soils, they would make these acres, which now scarcely yield them anything, turn out beneficial for themselves. Washington was arguing at the end of the 18th century for the urgent need for American farmers to reinvest in the fertility of their fields and to rebuild the fertility of their soils. He actually was forecasting in this statement the idea that American society would move across the Appalachians into the Midwest, not because of some innate tendency to expand the country, but because we were so degrading the soils of the eastern seaboard that for farming to maintain its viability, we would have to move to the fresh soils of the American Midwest. This is not something we tend to teach in our history classes. But if you go back and you study the history of erosion and its relationship to societies, these patterns start to become fairly clear. Well, so in researching the Dirt book, the first book of this trilogy, I really then became concerned of, well, how do you triangulate from this historical kind of anecdotal observations like the one from Washington that I was sharing? And you can trace that kind of stuff all the way back to Plato in classical Greece. So he recognized the effect of a Bronze Age soil erosion event that stripped the soil off the hillsides in classical Greece and actually limited their ability to support the large armies they needed to keep the Turks out at the time. So people have been thinking about soil degradation and its effect on societies for a long time, but there wasn't anybody running around collecting data in the Roman Empire, or the Greeks, or the Mayans, or the Chinese, or many of the other societies that had lost a lot of their fertile soil to this kind of a process. And so I became very interested in compiling contemporary numbers to know how fast are the world's farms eroding, how fast do soils actually build naturally, what's the kind of balance that we have at present. And I've boiled all that down to a single table. I actually wrote a paper in the Proceedings of the National Academy of Sciences that has all the data. If you're interested in it, just Google my name and this kind of stuff, and it'll lead you there. It's all in an Excel spreadsheet. Feel free to download it. Nobody should ever have to recompile this amount of data. What I did is I went to the library for a couple weeks when my grad students were all out in the field, and I sort of had the run of campus, and I could do something that whatever I wanted. I chose to go to the library, copy all the papers I could that actually had data of the nature of what are erosion rates off of contemporary farms, or farms farmed conventionally, and by that I mean plow-based agriculture for this comparison. I also compiled data from farms that were using conservation agriculture methods or no-till agriculture, that were not using the plow. It's the second line. Erosion rates under native vegetation, just how fast do natural landscapes tend to erode? How fast do soils tend to build under natural conditions? And then also very long-term geological erosion rates, really deep time integrations, because that's kind of a background against which you could test modern rates of soil erosion and soil formation. And I'll basically argue to you that that red number is really different than all those blue numbers. That's really the only point that I want to make with this slide.
What are the numbers in parentheses?
The numbers in parentheses are the number of independent studies that are averaged to make the number on the right. So basically you can see that there's something like 1,500, 1,400, 1,500 studies that were compiled in it. And there's far more data on conventional erosion rates, say, than a no-till back in 2007 when I wrote the paper. And what it basically shows you is that the bad news is that red number. Because if you basically look at the average erosion rate from farms around the world under conventional tillage-based practices, they're eroding at a pace somewhere around 1.5 millimeters a year, whereas long-term soil building is happening at the pace of about 2% of a millimeter a year. In other words, there's an almost 2 order of magnitude difference between the pace at which soils are bleeding off the world's agricultural landscapes and the pace at which soils being reformed. The good news is that blue number under the no-till label, because it basically shows you data from farms that is actually pretty similar. With this kind of a coarse comparison, the difference between any of those blue numbers is not something that I would argue was significant. In other words, that's where the good news lies, because the problem historically has not been that we farm. It's that we've been farming in erosive ways, and there are other ways to actually build soil. And that's where I'm going with the Growing Our Revolution book, because by the time I finished writing this dirt book, after compiling data like this, I was like, oh no, we are in deep, deep trouble in terms of the way that we have been practicing agriculture, and that it'll have to change this century. In writing Growing a Revolution, I visited farmers who have already made changes that demonstrate that we can expand the world of regenerative farming that could rebuild the world's soils. But let's first run the sort of the thought experiment that you can do with graduate students on the back of a napkin in terms of what do those numbers I just show you mean for the longevity of civilizations? Could the idea that erosive agriculture limited the longevity of civilizations in the past actually pencil out in terms of numbers? Well, if we take that net soil loss of about 1 millimeter a year, and I'm being conservative because the average number is about 1.5 millimeters, we just like drop that down to about 1 millimeter to be conservative. You could lose a 0.5 meter to 1 meter thick hill slope soil, a 1 to 3 foot thick soil on a hillside in about 500 to 1,000 years. To a geologist, that's screamingly fast. And it's also about the average lifespan of many civilizations around the world that were agriculturally based, with some really key exceptions. And those, of course, are the civilizations that thrived on big river floodplains, like the Tigris and the Euphrates in Mesopotamia, the Nile in Egypt, the Brahmaputra and the Indus in India. How can you forget the Indus from India, right? And then the big rivers of lowland China. Those are all areas where those civilizations thrived in the depositional floodplains at the bottom of the drainage basins, in areas where if you look at what was happening uphill on the margins of the Tibetan Plateau in the Himalaya and the Zagros Mountains in Mesopotamia, or in Sudan and Ethiopia in the Nile, the soils were being eroded off those upland areas and they were being deposited in those lowlands. So the societies that actually thrived for thousands of years under intensive agriculture with the plow were in the areas where all those soils were being eroded from the uplands and were basically ending up. So the exceptions to this time scale actually end up kind of supporting the argument. So the question that we really was wrestling with at this point was, is soil restoration possible? Could we actually reverse the historical trend? And this is something that I started to really have my eyes open to by how my wife restored our yard and rebuilt fertile soil in our North Seattle lot. She's a gardener. It's her passion. It's what she was one of those people who will be out gardening until midnight in the summer. And this shows you the soil that we started with back in 1997 on our lot in Seattle. This shows you the soil that we have today. We've basically converted it from something that was terribly infertile to something that is actually very fertile, and done it at a pace at which it really puts demonstrates that this can be done relatively rapidly. So as I was writing that dirt book, she was teaching me other ways to think about the soil and opening both of our minds to the idea that we could rebuild soil fertility very fast. And that was the impetus for writing The Hidden Half of Nature with Anne. This shows you her flame-enhanced wheelbarrow that was really one of the primary tools that we used to restore the soil in our yard, because we used it to gather up leaves from our neighbors. You can be you might not be surprised by how happy one's neighbors in a city can be when you show up with a wheelbarrow and rake up all their leaves in the fall and take them back to your yard. We basically realized when we peeled the lawn that our side yard came with, which was what I like to call it an old growth Seattle lawn, because it was basically nothing but grass and roots. We peeled it back and we found this really rich, fertile black earth. Now, we had glacial till, we had fill. We didn't find a single worm in that soil when we peeled that lawn off. Not a macroscopic life form. I'm sure there were some microbes in it. There might have been some fungi in it, but there was nothing we could see. And we were kind of distressed and realized that, wow, this dream of a garden that was going to be our nice special place at the side of our house wasn't off to a great start. And we realized that what makes for fertile soil is the marriage of geology and biology. And I should point out at this point that my wife is a biologist and I'm a geologist, so we're prone to thinking about stuff in that way. And we realized we had the mineral part of soil. What we didn't have was the organic matter. We didn't have the life in the soil, and we didn't have the dead life in the soil, the organic matter. And that's where that wheelbarrow came in handy, because that's how we started to bring back organic matter to the yard, first in terms of mulch and then in terms of compost, and then we got a worm bin and took all our kitchen scraps and filtered it through the worms and then put it back in the vegetable beds. We basically tried to scavenge organic matter from everywhere that we could to try and bring it back to the yard and start trying to build the soil up. And it only took a few years, 5 actually, more or less, to start recognizing some really big changes in our soil. This shows you Anne's pruning shears over here on the right with the soil pit that we eventually dug in the yard that, yes, we should have done before we bought the house to figure out what was in the yard before we thought about putting a garden in. But we sometimes get around to things a little late. And This shows you about, well, it shows you the wood chips and the leaves and the mulch that we essentially have been covering the yard with. We never rototilled the yard. We never dug anything up. We just started adding organic matter at the ground surface. And we would add a bunch in the fall, and by spring it would be almost gone. And after we got through the thought process of, well, who's been coming into our yard and stealing all our leaves? We realized that, well, it was who is now living in the soil and breaking it down and pulling it down into the soil. And then we started adding more on, and as fast as we could add it, it would be broken down. And after about 5 years, we still had that horrible, nasty till at depth. But notice that we've got about 2 inches here of relatively decent soil. Notice the plant leaves come down and they go sideways. They're not going down into that till. They're just growing in that relatively decent soil. So we had built about 2 inches of soil in about 5 years. That's about 4 inches in 10 years. That's almost a meter a century. That's way faster than nature builds soils. If it takes nature centuries to build inches, we are building meters in a century. This really motivated us to think about the question of, how is this all working? And when Ann and I started writing The Hidden Half of Nature, we thought we were writing a book about the problem and need for global soil restoration, which ended up being the Growing a Revolution book. But we got distracted by microbes, because the more we looked into the idea of how could we have transitioned this really poor soil into really rich, fertile soil so fast, the more we realized that we didn't do it. We enabled a bunch of microbial life to do it. And how did that work? A lot of that book goes into explaining how that works and the parallels with the human gut, and why the root system around a plant is really the human gut inside out, and the analogy actually works scientifically. But I'm going to spare you all that tonight in the interest of time, because as a professor, of course, I could just keep talking until midnight, and nobody probably wants that. But let me share a couple of the key things that we learned in writing The Hidden Half of Nature that we then sort of set up to go out and look at in Growing a Revolution. One of the things that really surprised me in looking into the zone of life around the roots of a plant, a zone called the rhizosphere, which is one of the most life-dense areas on the planet. We tend to think of, the Amazon or the Serengeti as really rich, biodiverse areas. Think about the root zone of a plant, because the diversity and abundance of microbial life is incredible. In terms of numbers of organisms per unit volume on the planet, it's about the highest there is. It's just mostly invisible life, so we don't tend to think about it. But in that zone of life, well, and this famous sort of picture of a plant coming up, all the yellow stuff are the roots of the plant. The white stuff that looks like the root system, that's the mycorrhizal fungi that are partnering with that plant. One of the things that we learned in researching Growing a Revolution was, it kind of astounded us, really, because it was the idea that really contrasted with what we had learned about the relationship between plants and soils in college. And we used to think of roots of plants as straws that were basically sucking nutrients out of the soil. And of course, that is to some degree true, but it's not the only role that roots, because it turns out that roots are actually a two-way highway. They're not a one-way highway bringing stuff into plants. Plants will actually push out through the root system exudates, or things they exude through their roots. They'll push out up to 30 or 40% of the material that they manufacture with their monopoly on photosynthesis. They'll push it out through the roots in the forms of carbohydrates, sugars, in terms of proteins. Even now there's a paper that just came out a few months ago that plants are pushing fats, lipids out of their roots into the soil. They're pushing food into the soil. They're pushing nutrition into the soil. Why wouldn't they use it to feed themselves after going through all the effort of turning sunlight and carbon dioxide and water into carbohydrates and the building blocks of plants? They're not doing it simply for the hell of it. They're doing it to feed that rich zone of microbial life that's around their roots. And they wouldn't be doing that if they didn't derive some benefit in return. And if you look back at the earliest fossils of plants that we have, they have mycorrhizal fungi intertwined with their roots. Fungi actually helped plants come ashore at the very dawn of life on the continents. The partnerships between microbial life in the soil and plants, in other words, are foundational to the ability of life to have colonized land in the first place. And you can think of, if these plants were feeding pathogenic organisms in the soil through all this stuff they're putting out through their roots, that's a really bad evolutionary strategy. It would not last. So they're deriving some benefit. And how does that work? That was what fascinated us in writing The Hidden Half of Nature, is getting into the science behind how that works. And we came to view the rhizosphere, that root zone, the zone of life around the roots of a plant, as a biological bazaar where microbes and plants are trading nutrients, metabolites, and exudates. And how does that work? Well, essentially, if you blow up the zone around the root of a plant, so you have this root tip coming in here with the big dark thing, the rhizosphere, that life-dense zone, we've colored in purple there. There's lots of bacteria in it. There's lots of fungi living in it. And the plants are pushing exudates out into the soil. Those exudates, those proteins, fats, and sugars, and they're even pushing things, those things disappear within about 1 millimeter to 1 centimeter because they get eaten. There's so much life there that's so hungry that they're basically eating all the stuff that the plants are pushing out into the soil. And what does any organism do with the stuff that it eats? It metabolizes it, and then it excretes waste products. What kind of waste products, or metabolites as they're known, are the microbes living in the rhizosphere producing? They're producing things like plant growth promoting hormones. Think about that. Bacteria, they're not plants, and they're producing plant growth hormones. They're feeding this whole other kingdom of life. So you have this system where the plants are pushing food into the soil, and those microbes living in the rhizosphere are functioning like little alchemical factories, little chemical factories where the plant has offshored the production of things that help the plant grow, things that help with plant defense. There's all this communication that's going on via chemical processes in the soil. And if you think about the problem of a plant defending itself, we all know about thorns and devil's club and things like that. That's obvious. But how else would a plant defend itself? By feeding little chemists in the soil that make things that then make the plant, that give the plant the ability to produce compounds that make it taste bad to herbivores, for example. There's all these partnerships in the soil that are every bit as evolutionarily fine-tuned and adapted as the kind of relationships we see between pollinators and flowers above ground at the scale we can see. That same level of interactivity is happening in the soil in ways that actually benefit the health of plants. And as we'll get to, the health of crops if we treat the soil right. And mycorrhizal fungi that essentially can grow in and both intertwine with plant roots and grow into plants, they will actually grow out into the soil with their hyphae, and they will excavate particular mineral elements out of soil particles, out of rock particles, things like phosphorus, copper, iron, bring it back, trade it to the plant in exchange for those nutrients that's getting through the root exudates. These are partnerships that go way back in geologic time and that are actually really important for the way that plants have evolved their nutritional and defense strategies. So the last thing I'll share from The Hidden Half of Nature is the way that Ann and I came to think about a plant's diet. We may not tend to think about plants having much of a diet, and you can make the same parallel for thinking about our own diet in terms of our gut, but I'll let you read that. It's in the second half of this book. But if we think about a plant that's grown in what we like to call a fertilizer diet, where you provide a plant with as much of the macronutrients that it needs, all the nitrogen, phosphorus, and potassium, for example, that it could take up. What will a plant do? Well, they kind of become what Ann and I like to call couch potato plants or couch potato crops. Because a plant that's fed a full dose of the macronutrients it needs doesn't invest as much in its root system. That means it's not putting out as many exudates into the soil. That means it's not feeding the microbes that actually bring those micronutrients or that provide the beneficial metabolites from processing those exudates. You're not getting as much of that back to the plant. That means you can grow big plants, but they may not necessarily be healthy plants. And there's a real reason that the growing use of and reliance on pesticides and insecticides followed hot on the heels of the growing use of major element fertilizers in Western agriculture. If you think instead about how you feed a plant the soil life diet, a plant that's grown in an organic matter-rich soil develops a very rich root system. It puts out more metabolites. You have a denser microbial community that's producing those beneficial metabolites that the plant gets back and a higher micronutrient flux as well. There's some very fundamental differences in how plants grow depending on what kind of a diet they get in the soil. That's the kind of thinking that led me basically to think about researching this new book, Growing a Revolution. Because it's one thing to think about restoring soil in your yard. It's another thing to think about, well, could we do this on farms around the world? Does it scale? Can you do it on little farms? Can you do it on really big farms? Can you do it? Do you have to farm organically to do it, or can you do it in a conventional system as well? Those are the kind of questions that I wanted to really ask, and the best way for me as a geologist to do that was to go visit farmers who had already done it and restored their soil and ask, what did you do? Show me your soil. Let's get a shovel and dig a hole in your field. Let's go to your neighbor's field. Let's compare them. And that's basically what I did. These two tubes of sampled soil over there on the right show you the result of how you can transform this kind of a soil into this kind of a soil based on the no-till farming trials at Ohio State University, where they've basically done this over the course of 20 years, and you can tell that there's a bit of a color difference. One of those has a lot more carbon in it, one is a lot more fertile than the other, and the one that is darker is the one where they went to no-till practices plus a cover crop and manure. They basically rebuilt the organic matter content of the soil. And the idea of rebuilding soil fertility, I'll submit to you, would actually be a very useful thing for sustaining intensive agriculture, which we will need to sustain into the future given the number of people we expect on the planet. How are we going to do that in a post-cheap oil and fertilizer world? This is something that if you think about how will we maintain intensive agriculture in 50 or 100 or even 200 years, we're going to have to think of different ways of farming than we do today, where we primarily depend on fossil fuels, both for powering all our machinery, but also for manufacturing fertilizers. And this led me to think about the potential for a soil health revolution. And that's the title of the book, Growing a Revolution. It's about thinking about agriculture through the lens of soil health and how that might be able to revolutionize agriculture, and what I'd like to think could potentially become the fifth agricultural revolution that humanity has pulled off. And by doing this, I visited farms around the world that had rebuilt the health of their soil and the fertility of their soil. And what I saw was that conservation agriculture principles could actually produce outputs that matched conventional farming and use far less oil and far less chemical inputs. And what do I mean by conservation agriculture principles? It basically boils down to three principles that the UN Food and Agriculture Organization has sort of laid out and identified as minimal disturbance of the soil, so direct planting of seeds, and those not tilling. Permanent ground cover, retaining crop residues and including cover crops and rotations, and diversifying rotations. Those are the sort of three elements that are defined as conservation agriculture. So I went around and visited people who had adopted all three elements to try and look at, well, how effective was that? And in case you're wondering, well, what is no-till farming? How could you actually plant seeds without doing that? This is an example of a no-till planter from a farm that I visited. You'll see David Brandt, this gentleman, again in a few slides in the future. But the basic way that it works is that you have a implement, a device that you can tow behind your tractor and put as many of these next to each other as you have tractor size to pull it. And there's a blade that spins at the front that basically cuts a trench into the soil. You drop a seed into that trench, and then there's things that cover it up on the backside. So it runs basically this way, and I walked along behind one of these as he was planting this field, and basically you can kind of see the disturbance in through there, but basically compare the magnitude of ground disturbance with this kind of a technique. You might be hard-pressed to even know that it's just been planted. Compare that to what you see after a pass of a freshly plowed field. And just in case, you know, given that I'm a skeptic by profession as a scientist, basically I followed along and said, okay, I want to make sure you actually planted seeds. Where are they? You could dig down. You find the little trench. There's this thin little zone of disturbance. And you can even sort of put fertilizer down right next to the seed if you want with another attachment on these things. So there's a technological way to essentially get around the practice of plowing with one of these no-seed drills or no-till planter. In terms of planting cover crops, there's other ways to think about that as well. Then the idea is to keep a crop on the field at all times, so you have the residue from the last crop, a cover crop growing in. One of the ways to think about how to manage cover crops is with something that's called a roller crimper, which is basically a steamroller-like device that has chevrons on it that you could put on the front end of one of those no-till planters. And basically, if you or going through a field that has a cover crop on it, you can knock down, crimp, and kill the cover crop with this crimper roller, and then it lays that crop down on the surface as a mulch that you can then plant right through with the no-till drill. This is essentially in a single pass, what farmers used to do multiple passes with, you can do in a single pass both the termination of the cover crop and the planting of the next crop. And what that has let some of these farmers that I visit do is they only take 2 passes of their tractor across their fields a year, once to plant and once to harvest. That saves them a lot of diesel. This shows you Dwayne Beck, the guy who runs Dakota Lakes Farm in Pierre, South Dakota. And you may have recall the cover of the Dirt Book, which had a piece of agriculture equipment from the Dust Bowl era in South Dakota with all the, sort of the classic sand blowing up on a piece of farm equipment. It's iconic photograph. It's from this area in South Dakota. And so I wanted to go back and visit Beck's farm because he has transformed the region into an area that is predominantly no-till. He took me on about a 300-mile driving tour around his region during what would have been plowing season and where there would have been black dust blowing across the roads anytime the wind blew. We saw 3 plowed fields in 300 miles in this area. He's basically, over the course of the last 30 years, demonstrated the way that no-till techniques can work to cut down erosion. He's then pioneered looking at crop rotations and using cover crops in this area. And he's done it through his demonstration farm that has a board of farmers that have all bought into it and sort of co-own the farm. And it's a research farm about how to actually adopt practices to build soil health at this point. And what he's done is by adopting no-till cover crops and complex rotations, he's reduced the use of diesel fertilizer and pesticides on farms in the regions by more than half. Some of the folks have reduced it by up to about 90% in some of those. That results in an obvious savings to the farmers because they're spending less on those inputs. But what happened to their yields? Well, compare those numbers. With the traditional yields, they're lower than what he's getting today with his complex rotation, cover crops, and no-till yields. They're basically increasing their harvest while reducing their expenses. And it took some time to rebuild the soil. There was almost everyone that I visited, including the gentleman that I'll be showing you in a few minutes, it took a couple years to actually start rebuilding fertility and get back to the point where they were equally profitable as beforehand. But the people who had run these kinds of experiments the longest were actually, and had rebuilt their soil fertility the most, were saving the most and had the best yields. You can consider it a long-term investment. Yeah. One of the interesting things, are you asking which are the competitive weeds?
Where are the competitive weeds out there?
Basically, if you look at their fields that they've been operating on at Dakota Lakes, there are hardly any weeds in the fields at all. There was actually one farm that I visited where they challenged me to find a weed. I couldn't. And that's one of the powers of sort of having cover crops in between their main commercial crops is that they're growing the weeds, terminating them, and so they're selecting which species they want to be in their fields. And they're selecting species that are actually pulling nutrients out of the soil, getting them in their bodies, and then delivering them back to the topsoil as they terminate them. And so there's a whole section in the new book on weed management, and there's some studies that are referred to in there from the Midwest that talk about a lot of the details of how they're thinking about crop sequencing to basically try and keep weeds out of their fields. And that was not something I was expecting to find. This gentleman is a guy named Kofi Boa. He runs the Center for No-Till Agriculture in Kumasi, Ghana, because when I was visiting Dwayne Beck, and he showed me that these practices could work on farms up to 20,000 acres, or the largest farm that I visited. I then asked him, well, could these work on small subsistence farms in Africa? Do you need all this technology to actually make this kind of stuff work? And he said, go talk to Kofi Boa. Just like, don't ask me about it, talk to Kofi, he's done it. So I flew to Ghana. Kofi was kind enough to show me around his farms. He works with subsistence farmers in the area around his village near Kumasi, Ghana. You'll notice his great Got Dirt, Get Soil hat that the Howard G. Buffett Foundation gave him because they helped support him develop his Center for No-Till Agriculture. And one of the ways that farmers there are actually increasing the diversity of their crops is not through the rotations in time, but also through the number of crops that they have in the field at any one time. Notice there's no bare earth. They're all no-till. There's a understory of several crops, peppers and other things, and then plantains. They have multiple crops in the same field at one time. The most I saw in any field is about 8, and they are mostly hand operated. There's not a lot of mechanization in these farms. They're mostly subsistence farms. And what Kofi has done by getting them to go directly from their traditional practices of essentially slash and burn agriculture to conservation agriculture, and skipping over the whole chemical intensive green revolution that so revolutionized agriculture in the 20th century, he's got them to radically cut down on erosion from their fields by a factor of about 20 or so. And notice what happened to their yields. Their corn yields tripled, their cowpea yields doubled. They did this with no fertilizer, with hardly any herbicide, almost no inputs. And why? Well, because these farmers they do not have the capital to buy into those kind of methods. And so this idea of using cover crops to reintroduce organic matter to the land and build nitrogen in the soil as a substitute for fertilizers really paid off for them, because this is something that had a direct impact on their lives. Before Kofi started teaching farmers in this village how to adopt these practices, almost nobody there owned their home. Today, almost everybody in the village owns their own home. This has had a huge impact. There's 2 more farmers I'll share you a little bit about. Gabe Brown over there on your left, David Brandt over there on your right. Gabe is a North Dakota farmer who runs both livestock and a cropping operation on his farm. He has a CSA that he's developing with developed with a market garden, and where they have both cattle and pork and chickens. And David Brandt, on the other hand, his livestock is all below ground. He's in Ohio, and he grows corn and soybeans. He's a conventional commodity crop farmer, but he also grows a lot of cover crops, and including one of his favorite, his radishes, which he basically says they are what till his soil for him. And he doesn't harvest them. He was kind of pleasantly surprised, or maybe a bit shocked by what I told him we might pay for a radish like that in the farmer's market in Seattle. But he said he won't sell them. That's the food for his microbes. That's what he feeds his livestock. He just rolls over them with one of those roller crimpers, or terminates the crop otherwise, lets them rot in the fields. And he's actually done the nutrient testing of what you get, and those radishes are creating little phosphorus and nitrogen hotspots in his soil. It's basically one of the ways that he pulls nutrients out of the subsoil, gets it in the topsoil, and then in the next cycle gets it into his crops. So what's he done? I want to walk you through the economics of his farm, because one of the things that was, I thought, so optimistic about these farmers that I visited is that they were all doing better economically than their conventional neighbors, because they were spending less to grow more after they had converted their practices in ways that built up the fertility of their soil. So David Brandt, he's near Carroll, Ohio. The county average, as he reported it it was 2 years ago that I basically was out interviewing him. Most of his neighbors are full tillage. They apply about 200 pounds of nitrogen and 2.5 quarts of Roundup per acre on their farms, at a total cost of about $500 an acre, which that year their average yield is about 100 bushels of corn an acre, so they were losing about $100 an acre for all their hard work. That's not a really good economic model. One of the studies that I ran into in finishing this book was the next year, 2015, in Iowa, I believe it was, 24% of the farmers there lost money on every acre they planted because they were spending so much on inputs and getting so little for their harvest. And that is the great irony of modern agriculture across much of the Western world, much of the United States, is that farmers have become so good at growing things that they've depressed the price of what they get for their harvest, but the expense for all the things that we tend to rely on in conventional agriculture has gone up and up and up, and it's the farmers that are squeezed in the middle. What Brandt was doing, though, he's been no-tilling for 44 years, ever since he came back from the stint in the Marine Corps in Vietnam, and he has then adopted cover crops and has now diversified his rotation. So he didn't adopt all 3 of these practices at once. He worked his way into it, as did all these other guys that I've been talking about. And He doesn't till, he uses about 24 pounds of nitrogen and 1 quart of Roundup an acre. He's not an organic farmer. He's using fertilizer and he's using herbicide. He's just using 1/8 of the fertilizer and 1/5 of the herbicide as his neighbors are. And he's spending about $320 an acre to growing about 80% more. This translates into a net profit at $4 a bushel. He's making about $400 an acre, while his neighbors are losing $100 an acre. Which farm would you rather have? It's a really good question that I don't have the answer to, so you might not want to ask me as to why all his neighbors aren't doing this. But there's a lot of barriers to people adopting things, not the least of which is new thinking, new ways of doing things. Question? He's using the same seed. So his basically, his total cost, these costs include that, but he's basically using the same GMO seeds as his conventional neighbors. He's starting to experiment with using some organic seeds and other kinds of seeds.
But his cover crop.
Are the other guys cover cropping too?
No, the other guys are not cover cropping. So his cover crop seeds are included in there, but it's pretty minor. And he's actually started, he's basically he gets his own, anyway, he's doing his own seeds for cover crops. He's actually selling cover crop seeds to other people as well as a side business. But the costs up there are sort of integrated costs, as he reported, because I haven't looked at his books, but he's a very honest guy. Gabe Brown, the other guy I was talking about, he likes to show off his soil to visitors. He plants very diverse mixtures of cover crops in his fields in between his commercial crops, but he also uses livestock. And those of you who have read about Joel Salatin's farm and his sort of use of livestock and chickens, Gabe's doing something very similar in terms of he will have his cattle graze off the cover crops. So he'll grow a conventional crop, he'll then plant a cover crop, his cattle will come in and graze off the cover crops, and then the chickens come around and graze off the bugs that are in the cattle poop. And they basically are, you can think of them as, well, the way I think of them now is as an accelerator for breaking down the organic matter that was grown in the cover crops and returning it to the soil so it's more readily available to the next crop. And what's it done to his soil? Which one do you think is Gabe's soil? Yeah, the one in his right hand, that rich sort of black one, is his soil off of his market garden, which has received sort of special attention, so it's some of his best soil. The soil in his left hand, that's his neighbor's soil from his neighbor's organic farm. Yeah, his neighbor's organic tilled farm. So basically, this sort of brings up questions of, if you're thinking about prioritizing soil health, Gabe is not an organic farmer. He's just not using much of any herbicide or fertilizer. And he's really rebuilt the fertility of his soil. And that just gives you the direct on comparison of the two again. One of the things that I found personally so enlightening in terms of visiting North Dakota and talking to both Gabe and also people at the Natural Resource Conservation Service, in particular Jay Fuhrer, who's shown here, is that I sort of went through on a demonstration tour for farmers that came to Minokan Farm, their demonstration farm, and he likes to show a sprinkler experiment where you take different kinds of soil, and I'm going to focus on this one, which is conventionally plowed soil, conventionally tilled, and this one over here, which is no-tilled with cover crops and a diverse rotation, where he's basically extracted blocks of the soil. They're in these trays, which are open on the bottom, and they have a collector on the top. So when you rain on it, water that falls on it and runs off over the surface goes into one bucket, and water that sinks through the soil goes into the next bucket behind. And we're just going to look at this soil and this soil. These three are different kind of grazed fields, as I recall. It's not the comparison I want to draw your attention to, although if you want to check it out, that's perfectly fine. It's just a little extraneous to the points we're talking about. But as you rain on these soils, notice what happened to the tilled field. You got a whole lot of soil that came off in runoff. Nothing sank into the soil. One of the rationales for tillage that I keep hearing is to basically open up the soil and get water to sink down into the soil. But it doesn't really work that well. Why? If you bust up the soil and you bust up its structure and you kind of powder it, soon as you start getting rain on it and gets wet, the surface will crust up and the next rain will run off over the surface. On the other hand, this no-till soil, there's hardly any runoff. Little organic matter, not a lot of soil in it, and the water that sinks down into the soil, notice it's a different color brown than this water. It's mostly organic acids that have been leached out of that surface and are going down into the soil, delivering carbon and organic acids down into the soil profile. Most importantly, you're getting water that's actually sinking into the ground where you want it as a farmer. You don't want it running off over the surface. You want it in the root zone of your plants. And when Jay runs an experiment like this, I was fascinated to be sort of seeing people react to it and farmers going, wow, look at that, look at the color. You know, this is like completely counterintuitive to how they'd been trained to think about what tillage was doing for their farms. And so basically I tried to sum up the basic ideas behind conservation agriculture with the idea of ditch the plow, cover up, and grow diversity. It's those three elements together that really seem to be the recipe for building soil organic matter and building soil fertility. It's basically, I think, the recipe for feeding the microbes in the soil, for cultivating beneficial soil life, which then does the work of restoring the soil. What are some of the benefits for adopting these kind of practices? With or without livestock, there's different ways to actually do it, and I should basically advertise that those three general principles seem to translate into different environments, different settings. They scaled, but the actual practices, the specific practices you would use, say, in Ghana and the Dakotas are totally different. So I think one of the key things in adopting these ideas of conservation agriculture is figuring out how to adapt those general principles to the local reality of the soil in a region, the kind of crops that are grown in a region, the market for those crops and the sequencing of that, as well as the technology available to farmers. There's a lot of innovation that needs to happen, and I think in conventional agriculture, we've basically made the mistake of trying to make the soil adapt to a uniform set of processes, intensive tillage with intensive chemical fertilization and monocultures, and whereas what we need to do is flip all three of those on their head to go with ditching the plow, covering up, and growing a more diverse set of crops. And we need to take advantage of the innovative abilities, the ingenuity of farmers to figure out how to adapt those general principles to the specifics of their farm. Because I think the kind of benefits we can harvest are comparable, if not increased yields, greatly reduced fossil fuel and pesticide use, increased soil carbon and water retention, and that water retention translates into crop resilience to droughts. So there's two connections to climate there, whether we're putting carbon in the ground and whether we can actually keep our crops healthier as the climate gets a little more challenging. And what was most exciting to me was that it can basically improve on-farm economics and result in better profits for farmers, which I think will help revive smaller family farms in rural parts of North America where a lot of towns have been kind of hollowed out. You drive across the Midwest today and far too many towns have been hollowed out over the last 50 or 80 years, and we need to, I think, rebuild the economic model of small farms, and these practices, I think, are one step on the way towards doing that. And it's not really a question of low-tech organic versus GMOs and agri-tech approaches. I think that's sort of a false dichotomy in some regards. Particularly in regard to these issues of soil building practices. I think you can do it both in conventional systems and you can do it in organic systems, because those three principles you can do them in either kind of a system. We need, in other words, to understand soil ecology and apply it to the problem of increasing and sustaining yields in a post-oil environment. The climate connection is one that I think is really interesting and really strong and actually could help drive some of these changes. But if you actually look at the range of estimates that people have offered for how much carbon we could park in the world's soils as a result of adopting these practices, you get estimates that are frankly all over the map. Down from the low end of a very conservative range of estimates that the eminent soil scientist Rattan Lal has offered of maybe 5 to 10 to 15%, call it 10% of global fossil fuel emissions for several decades, if not 50 years. That's at the low end, and I'd like to point out that that's still a very significant number. That's a lot of carbon. At the high end, people like the Rodale Institute have estimated that you could fully offset fossil fuel emissions. Personally, I happen to think that the realistic number is between these two, probably around a third to a quarter to a third, maybe a little bit more. But the point is that if you basically adopt these principles of conservation agriculture with the goal of rebuilding soil fertility, the carbon benefit comes along for the ride. It's the same practices to improve the fertility as you would do to sequester carbon in the soil. It's a win-win. And so I think that thinking about, and the way to think about this is, I think that thinking about agricultural practices through the lens of building soil health, of actually rebuilding the fertility of the soil, cultivating the beneficial life in the soil to do that, and that we need to use the insights of soil ecology to restructure agricultural technology to build soil health. It's a way, I think, the way I like to characterize it is we need to take some of the ancient wisdom behind the ideas of crop rotations and cover crops, which are ideas that were traditional in many parts of the world because they helped enhance soil fertility. We need to take those ideas and marry them with the modern technologies that allow us to actually pursue no-till practices in different regions and marry that ancient wisdom to modern technology. It's not a choice between the two. It's about taking the best pieces of both and putting them together to build a new system of farming, a new philosophy of farming that prioritizes rebuilding the health of the soil. And that's going to take some ingenuity. It's going to take thinking about how to apply these general principles to different areas. I'm not telling you that what the folks did in Ohio, Ghana, or the Dakotas will work out here in the San Juan Islands, but I think it will be a challenge to figure out how those practices could work here. But from what I've seen around the world, there's a recipe. You just need to figure it out. Other kind of things, we could reform crop insurance and subsidy programs. We could establish demonstration farms to basically pursue some of those research agendas on a farm where someone's not betting their farm on the outcome of a particular crop, but that the mandate of that farm was to experiment and support other farmers. And we could also think about providing transition assistance for those several years where it takes to actually start getting the soil to rebuild its fertility. There's a critical period in there. Not everybody could necessarily afford to weather that transition on their own, but it's in society's best interest, I believe, for us to encourage more farmers to do that. And at present, we're subsidizing the destruction of soil with our agricultural subsidies and practices at a national level. We need to flip that around, and transition assistance to farmers who could then become more profitable and self-sufficient, to me, sounds like a really good societal investment. At the bigger scale, why might we really want to think about what I like to call as the world's biggest infrastructure project, rebuilding the fertility of our agricultural land? It would help us feed the world. It would help us manage climate change and sequester some carbon. Estimates may be all over the map, but the sign of those changes is known. It would enhance biodiversity and reduce environmental degradation. And if you look at the future of biodiversity in this world, something like 1/4 of the continental land masses are in agricultural land. Any way you cut it, how we manage biodiversity on farms is going to be a big piece of the future of biology. And we could restore, I think, profitability to family farms, or at least make farming a more profitable enterprise by reducing the input costs while maintaining harvests. I'll leave it there. I obviously recommend all 3 books to people, but of course you knew I would do that. If you're into social media stuff, Ann and I are on Twitter now with a handle @dig2grow. If you want to ask us other questions, feel free to email us. We have a website that if you want to dip into any of these books and see what is the argument or behind them, or see some of the reviews of them, go check it out. We obviously encourage you to do that. And we also encourage you to visit Griffin Bay and pick up a copy of the new book that they have here tonight. And I'll thank you for your attention. I think we probably have time for a couple questions, and we'll start with you.